Let's talk about rolling motion, which is a special type of motion that combines both translation, which is moving from point A to point B, and rotation, which is where, well, it's rotation. It's an object where the different parts of the object are moving around a fixed axis. So talking about kinetic energy, what we've worked with before is translational kinetic energy. It depends on the mass of the object and its velocity. And we have the formula, familiar formula, 1/2 mv squared. Now, I've updated that slightly by putting a subscript t for translational on it. Now, an object also has energy just because by rotating, right? You can imagine um, if somebody was held up a spinning bike wheel, spinning around its axis, or a spinning top, you'd have to do some work on it to get it to stop. So if we just look at the rotational motion of the wheel, right, not considering it rolling, but just rotating around a fixed axis, well, we can figure out what the equation for the rotational kinetic energy should be just by comparing to the translational one, right? So we still have the 1/2. Now, for translational, we have mass, which is basically a measure of how hard it is to get an object moving. So we have a value I, moment of inertia, which is basically how hard is it to get an object rotating. And then rather than the translational velocity v, we just replace that with the angular velocity omega. So that would be in radians per second. So how much of an angle does that object rotate through every second? Now, if we have rolling, we're going to talk about a very specific type of rolling, which is called rolling without slipping. So that will allow us to relate translation and rotation. So now if we look at this bicycle wheel, which is rolling along to the right, the center of mass has a certain velocity, right? So if you were riding a bike that was attached to this wheel, that would be how fast you're moving, right? But different parts of say the tire are rotating at different speeds compared to the center of mass. The point at the top of the tire is also rotating, or because of its rotation is moving forward even faster than the rest of the bike. And the part that's at the bottom is rotating backward. Now, what's key about rolling without slipping is we can say that point that's at the bottom that's touching the ground, it's momentarily stationary, right? So that and that should be familiar to us when we were talking about friction problems, and we were trying to figure out, a car driving around a curve and do the centripetal motion and centripetal force problems. We were always using static friction because the car's tires are not skidding, right? So the part that's touching the ground is not moving either forward or backward. So we can figure out then that means that the center of mass velocity, the velocity of the bike, has to exactly cancel out the backward velocity that the bottom part of the wheel gets from the rotation, right? And we can also calculate that rotational velocity based on the angular velocity just by multiplying by the radius of the wheel. So that capital R there is the radius of the wheel. And when we do that, that lets us see that the rotational velocity has to be equal to the center of mass velocity. So we can write that now, since we know that those velocities are the same, we'll just drop the subscripts and we can say that for rolling without slipping, the translational velocity is equal to omega times r. Right? So that allows us to do a lot more with these problems than if it were, say, a wheel that was rotating and slipping. We don't have enough information to deal with that. Okay, so let's put this idea to the test. Right, here's we're going to show a race between two different objects. One is a rolling hoop and one is a rolling solid disc.
Here I've got two discs which have the same radii. One of them is an aluminum ring, and the other is a piece of wood. Now, if these have the same mass, they have the same inertia, but they don't have the same rotational inertia because that mass is distributed in a different way. For this, the mass is distributed uniformly throughout. For the ring, the mass is all distributed far from where the axis of rotation will be, which is going to be right through the center. And so this will have a greater rotational inertia than this wooden disc. What we're going to have them do is race down this incline. And the one with the greater rotational inertia will lose the race because it will have a greater resistance to a change in its state of rotational motion. So the wooden disc rotated more quickly and won the race down the incline. That makes sense because we said that the metal ring had greater rotational inertia, so there's a greater resistance to a change in its state of motion.
So now let's look at how we can mathematically solve that problem to show that the solid disk would win the race versus the hoop. All right, so because it has a greater velocity at the bottom of the ramp or at any point along the ramp. So let's look at the total kinetic energy of a rolling object. We know that it's going to be the sum of the translational kinetic energy and the rotational kinetic energy. So we can plug in the expressions that we know there. So that gives us 1/2 mv squared plus 1/2 I omega squared. Now, in general, for any of these sort of circle-based shapes, the moment of inertia is going to be proportional to the mass of the object and the radius squared. Right? And then A is just going to be some number that depends on the shape. So for a hoop, it's 1. For a solid disk, it's 1/2. For a solid sphere, it's 2/5. Right? So that would be something that you look up in a table to figure out exactly what that number is. So we'll keep it general and we'll just call it A. Now, I want to note that that's not a standard notation. It's just something that I'm inserting here. Different people use different things when they analyze this problem in general. So I can plug that in along with the fact that I know that omega is equal to V over R, right, for rolling without slipping. So I just slightly rearranged the formula that we saw before. But the reason why I do that is because I want everything in terms of velocity. I don't care who's rotating the fastest. I care who's moving the fastest. Right, so making those substitutions in the rotational kinetic energy, we get this expression. So we've got 1/2 mv squared plus 1/2 a mr squared times v over r quantity squared. Now, you might notice there that in that second term, there's an r squared divided by r squared. So we can cancel those out. So that's interesting. It shows that this kinetic energy calculation does not depend on the radius of the object. So simplifying that here, we get 1/2 mv squared plus 1/2 a mv squared. And if you're like me, you see these like terms and you want to factor things out. You don't necessarily have to if you're just going to calculate. But with this algebraic expression, I think that looks nice and understandable. So what that tells us is that we just need to look up this factor of A in order to solve this, or to figure out the total kinetic energy. Now, what does this mean from a practical point of view? How can we tell which object is going to win the race? Well, we know that both objects start with the same potential energy, right? They start at the top of the same ramp. So the question is, which of these objects is going to waste less of its kinetic energy on rotational motion and use more of it for translational motion? So you want A to be as small as possible to go as fast as possible. Right, so that's why we see that the solid disk beats the hoop, and the solid sphere would be faster than both of those. The other reason why we can also see that the mass again is likely to cancel out because if you have a potential energy, well, that's going to be dependent on the mass of the object, so the mass would cancel out in the end, which we've seen in lots of different situations. Now, we got one more race to look at, a race of different radius solid spheres. So which one do you think would win the race? The largest one, the one with the largest radius, or the one with the smallest radius?